An important tool in reservoir characterization is seismic inversion, which enables you to combine well and seismic data to predict rock properties across the survey, such as lithology, fluid content, and porosity. These rock properties can then be used to help identify hydrocarbon targets and reservoirs. While many of these rock properties can be identified at the well using log data, rock properties such as fluid content, lithology, and porosity are difficult to obtain away from the well using seismic data. However, with seismic inversion, we can obtain other rock properties such as impedance and attributes derived from impedance, such as Poisson's ratio, BPVS, lambda rho, and mu rho. These impedance attributes are linked directly to fluid content, lithology, and porosity. For example, if we cross-plot porosity and acoustic impedance, or P-impedance, and color the results by lithology, in this case we'll use shale volume, you can observe a relationship between P-impedance and porosity for different lithologies. This tells us that for a given lithology, if we know the acoustic impedance, we can get an idea of the porosity value and the uncertainty on the estimated porosity. Similarly, let's create a crossplot showing acoustic impedance versus Poisson's ratio, which can be used as an indicator of hydrocarbon content, color-coded by shale volume. Here we can again discriminate lithology based on impedance and Poisson's ratio, and if we now color code the data using water saturation, we can pick out the hydrocarbon discrimination line. So by using both P-impedance and Poisson's ratio, you can get an understanding of both lithology and fluid content. From these crossplots, you can see that if we can combine impedance information calculated at the wells with impedance calculated from the seismic data, we can predict hydrocarbon targets across the survey, not just at the well locations. Since impedance is simply density multiplied by velocity, and Poisson's ratio and other attributes can be calculated from impedance, we can easily obtain impedance, Poisson's ratio, and other attributes at the wells using density and velocity log data. But to obtain impedance from seismic data, we need to use seismic inversion, which converts the seismic data from a boundary property to a rock layer property. While well data shows us information about the properties of the rock layers, seismic data shows us information about the boundaries between rock layers. That is, changes in fluid content, porosity, or other properties within a rock layer will show up as changes in the seismic amplitude at the interface between the layers. With seismic inversion, the seismic data is transformed into layer properties, such as impedance. This allows us to confidently extrapolate in 3D what we can see at well locations to aid structural interpretation across the survey. We can also analyze these rock property volumes using cross-plotting tools, just as we did with the log data, to identify prospects far away from the wells. So, how does seismic inversion work? The inversion process removes the imprint of the wavelet from the seismic data in a deconvolution process and then converts the results to impedance. The process is often guided by a background model. So, for most inversion methods, the first step is to tie the well data to the seismic and estimate a wavelet, or multiple wavelets depending on the type of inversion you're performing. The next step is to extrapolate the well data across the survey in 3D, guided by the interpreted horizons. This creates the background model, which is used to ensure that the impedance values are realistic. The background model contains no seismic information. The third step is to perform the inversion. And then the last step, of course, is to interpret the results. Not all inversion methods require you to extract a wavelet or create a background model. So, depending on your goals, you can perform a simple and quick seismic inversion to create relative impedance data for interpretation work, or perform a more rigorous seismic inversion for detailed quantitative analysis. The simplest inversion method offered by Paradigm is colored inversion. This method is very easy to use, making it accessible to the general interpreter as well as the QSI expert. It uses a single post-stack volume and creates a single impedance volume. Instead of a wavelet, colored inversion calculates its own inversion operator based on the frequency of the seismic and the well data. Colored inversion can also be used when no wells are available, and it can work with or without a background model to guide the impedance values. Paradigm offers several other post-stack inversion methods. Like colored inversion, all of these post-stack methods calculate a single impedance volume from post-stack data. However, since these methods use a wavelet for the deconvolution, the results are generally more refined than the colored inversion results. Post-stack inversion generates a single impedance volume, usually acoustic impedance. This is useful to QC your interpretation, where the horizon you're picking is the top or base of a rock layer. It can also be used to understand the lateral variation of porosity in a sand layer, for example. But if you want to determine lithology or fluid content, you need to analyze the acoustic impedance along with another impedance attribute that incorporates shear information. To obtain multiple impedance attributes, we usually use pre-stack inversion. The pre-stack inversion methods offered by Paradigm are simultaneous inversion methods, which are rigorous model-based methods that generate the acoustic and shear impedance attributes simultaneously. Both of these methods can use multiple wavelets for different angle ranges or a single global wavelet. The pre-stack maximum likelihood inversion, or PMLI, enables you to use gathers as input and includes options for performing on-the-fly gather conditioning during the inversion process to optimize the input gather quality. Paradigm also offers a log curve prediction or neural network inversion, which can be used to generate log attribute volumes such as porosity and water saturation. Instead of using a wavelet, this method uses neural network technology to create an operator which ties the log data to any post-stack volume. Unlike other inversion methods offered by Paradigm, the input post-stack data can be any attribute, including rock property attributes generated through other inversion methods. Although this inversion method doesn't require a wavelet, it does require a lot of wells, and the wells need to be carefully tied to the seismic in order to estimate a stable operator. Paradigm is pleased to offer a robust and varied set of inversion methods enabling you to convert seismic data, which describes lithologic boundaries, into rock property attributes that describe the lithologic layers and can be used to aid structural interpretation and identify hydrocarbon targets in the subsurface.